Did anybody notice that I got 30 minutes from my talk? I asked Kyle about that.
About 20, but you always overrun.
That's what he said. He said it was by design, and I think his exact words were, Jack's a bit of a talker. So, Begonia, David, Jeff, you have your excellent scientific credentials, but you only got 20-minute talks. If you're long-winded, you get a 30-minute talk, apparently. I do have a lot of slides, so I'm going to get right with it. You see, I do have a catchy title, and I hope I can prove something to you about injection technique that may work for you as Thermo makes the instruments more and more sensitive, which I'm sure they're going to do. I call it Shoot-and-Dilute Gc MSMS, and it's analogous to doing Dilute-and-Shoot for LC MSMS. And at the risk of actually losing credibility immediately with the audience, I, as a GC chemist, am going to venture into LC world and tell you why Dilute-and-Shoot works so well. With electrospray ionization, APCI, you have problems with ion suppression enhancement, especially when you have dirty or complex samples. And this, of course, leads to poor detectability and sometimes very significant quantification bias. And you can't just sweep all that away with isotope dilution because there's just too many things to analyze, especially in the pesticides and food world. Offline cleanup may help, or you may get by with selective LC columns to retain things a little bit longer. But what a lot of people do, and we've been able to take advantage of the fact that there are more sensitive instruments on the market, it seems like every day in the LC world, is actually dilute their sample down and shoot it. They dilute it in mobile phase and shoot it. And of course what this does is you dilute the matrix to the point where it doesn't negatively impact the detector. Now, I include the ionization technique in the detector when I say that. I don't specifically mean that the MSMS is impacted at all, but the ionization technique certainly can suffer when you don't dilute and shoot with LC MSMS. And again, I want to tie that to great improvements in instrument sensitivity. It's why we use it so successfully in LC. Analysis with GC is a bit different because problems happen on the other end. You have the GC inlet system, which is kind of the weak link in the whole system. If you think about an expensive high-res mass spectrometer able to detect femtogram levels of components, it doesn't do you any good at all if you can't get it through the gas chromatograph. And especially in the pesticides and food world, we have problems with active, polar, thermal sensitive analytes, dirty samples consistently. We can either have matrix enhanced or degraded responses, significant quantification bias, limited transfer from GC inlet to column, which I'll show you a way that we can overcome that, poor detectability, and you can get some relief if you do offline cleanup, but who wants to do that? So what I'd like to suggest to you is as the instruments get more and more sensitive, or as you can do it to meet your needs, your limited quantification, limited detection needs, you could potentially use split injection. And that's because you can actually dilute the matrix effect out on the front end and get some benefit to actually get analytes more successfully, more proportionally successfully to the GC column and eventually the detector. And they kicked me out of the marketing department probably for coming up with this catchy name, but I call it Shoot-and-Dilute Gc. Basically, you shoot it in and dilute it by splitting part of the sample away. And there's a reason that we want to do this, and I'll talk about it more. It also relies, like LC-MSMS, on detector sensitivity and selectivity improvements, for example, MSMS. Is it too late in the afternoon for cartoon characters, folks? Believe it or not, this was called the Banana Splits. It was a TV program when I was a kid. And usually the first thing that happens is somebody screams out, they only had black and white TV when you were a kid. But that's not the case. They did have color TV. And one of these characters is asking, why should I do split injection for organochlorine pesticide analysis? Of course, the ECD that we use, and we do a lot of ECD work in the US, is very sensitive. You can start at a higher GC oven temperature so you can increase your throughput. Instrument uptime and theoretically GC column lifetime will be better. Split injection approach works great any time that you don't need the absolute ultimate in sensitivity. It gives you some benefits that you may not have thought of. And particularly, I want to get right to that right now, and that's a much faster inlet flow, which helps reduce degradation of sensitive pesticides or thermally sensitive things. This increased flow through the inlet is very good at helping that out. Most of you are doing splitless work and are using a regular splitless inlet are probably using a liner that looks somewhat like this. A single taper liner. It may have wool or it may not have wool. And probably all of you have experienced this problem where we have let the liner stay in a little bit too long or the samples are a little bit too dirty. And before you know it, the wool is contaminated and we're not having any of our analytes make it through to the inlet, or they're breaking down as a result of contacting that dirt. When we do split injection, and I'm showing you what we call a precision liner right here, the goal is for only part of the sample to make it to the column. We do want the analytes that we're directing towards the column to make it there intact, and again, split injection has some benefits for doing that. In this particular case, this precision liner, and let me use this laser pointer here, has a wool plug right here that actually wipes the autosampler syringe needle, and this leads to great repeatability, injection after injection after injection. The first application I'm going to show you is one that we do routinely in the U.S. It's EPA method 8081B. It's a GC-ECD analysis of organochlorine pesticides. Restek sells about $1 million of columns a year for this particular analysis, believe it or not, and no telling how many liners and seals and other things to support it. So it's quite a significant part of our business. And we talk to customers who are down all the time as they try to implement this in their lab, and it's mainly because of these dirty samples that I'm talking about. The data, the first data point is right here, and that is we actually were able to demonstrate extremely low endrin and DDT breakdown, which is a criteria of actually performing this particular methodology, just by using a split injection. And you can see at a split ratio of 50, the inlet split flow is 125 mils per minute. Splitless, you're usually around 1 or 2 mils per minute. So the residence time of the endrin DDT is extremely short, and that pays off in not seeing a lot of endrin breakdown. Now, in the case of 8081B, it specifically says if you don't have less than 15% breakdown for endrin DDT, you have to take corrective action. And of course, you know what that means. If you're a gas chromatographer, you're changing your inlet liner, you're changing the bottom seal, you're trimming the GC column, and all of that is downtime and money and potentially loss of resolution between closely eluting compounds, et cetera, et cetera. A better way, perhaps, split injection. Here's an example of a group of organochlorine pesticides that we routinely analyze for in 8081B, and looking at a split ratio of 50, I'm actually able to start the oven at 180 degrees C. That's one of the benefits, using hydrogen carrier gas, and I basically have all of these components resolved in less than 5 minutes. So we've got a pretty fast analysis here, but really we're focusing on split injection. Now we can do this very repeatedly, as I mentioned, when we use this type of liner, because the wool is positioned that it wipes the liquid droplet off of the syringe needle, and this leads to great reproducibility. This is an overlay of 7 back-to-back injections for a group of organochlorine pesticides, and I've just zoomed in on a few of them, and as you can see, the actual overlay is pretty tight. Calibration curve looks good even when we're actually operating at relatively low standard concentrations here, and approximately at a split ratio of 50, we're putting 40 femtograms on for this low point and 4 picograms on for the high point. These are triplicate analyses right here, and I've just used lindane as an example of how well you can do when you consider that the ECD is super sensitive. And these are real peaks here. They're not just phantom peaks, to steal from Patterson's slide. They're actually real peaks. You can see this is 40 femtograms of the BHCs right here. These are nicely formed peaks, nicely detected peaks. So we even have some room at the bottom for these particular components. And we're doing this again with a 50-to-1 split ratio and getting a 2 to 2 picogram per microliter concentration. Now don't look at all of this table. I'm just going to sum it up for you, that at least for this group of pesticides, we could actually produce very linear calibration curves, and the response factor RSD percents easily met the 80-81B criteria. And this is with a 50-to-1 split injection. We did the same thing with a 10-to-1. If you happen to dip down further, we had to start the oven at 150 degrees C in that one to improve the peak shape for tetrachloroamxylene. But it works quite well, and it can be employed in other cases. Now, it's funny, when I talk to customers about this, one of the first things they ask me, and these includes customers that are down all the time from injecting dirty samples, is it rugged? And I'm thinking, well, I just introduced 50 times less dirt, if you will, to the GC column, et cetera, so I think it's going to be rugged. But they don't want to hear that. They want you to prove it, and I think that's a legitimate thing to do. So what I did was I took used motor oil as a surrogate for a dirty sample and started interspersing it between standards analyses, particularly the Indra DDT breakdown test standard, to see if a system could hold up when I'm doing the split work. I expected it would hold up for some period of time, but I didn't know how long. Now let's just revisit what actually unacceptable Indra DDT breakdown looks like. This was only Indra and DDT injected into a dirty liner, and you can see already we have very unacceptable breakdown. 80-81B says do not proceed. It says change your inlet liner, maintain your inlet, seal, column trim, etc. But that's what unacceptable breakdown looks like. Used motor oil. It's got this stuff in it, and it's got heavy, non-volatile material in it. But the other thing it has in it is metals, and metals are notorious for breaking down Indra and DDT. So I think this was a relatively well-chosen surrogate to approximate a dirty sample. Now, believe it or not, we sell a used motor oil composite standard, which I always thought was kind of crazy, but I could actually go out and get a sample right out of the back of used motor oil. And it's interesting because it's prepared from an equal volume blend from 5 gasoline-powered vehicles belonging to Restek employees. Now that's great, isn't it? So, yeah. I assume that we went out with an autosampler vial and filled it right up, but that's probably not what really happened. Here's the 5 Restek employees broken down on the side of the road after they had their used motor oil drained and nobody told them. Okay, now, whoops. Okay, if we look, this was something I had to do, but here's the list price for that. That doesn't seem too bad for a standard, right? But if you look at a local shopping place like Walmart, and you consider it $16.47 for 5 quarts, by the time you calculate this all up, we're almost charging $3 million for 5 quarts, and that's used motor oil. Which I think, Ben Priest, you're wasting your time with all these expensive labeled standards. The money's in used motor oil, man. Okay, now my friend Steve Wise, who works at NIST, told me about this newspaper article, which I thought was hilarious, pricey samples from BP oil spill being sold to scientists. And if you look close, it says it's likely to be one of the oldest ironies to emerge from the BP oil spill. The federal government is selling tiny containers of oil siphoned from the Macondo well at a price equal to $76.3 million a barrel. By comparison, a barrel of crude oil was selling for $106 on Wednesday. Now, I'm not sure who the biggest thief is, NIST or Restek, really. Okay, so here's my experiment. No problem here at the start of the experiment. This is what we expect, right? Split ratio of 51, easily meet the Indra and DDT breakdown criteria, 37 injections of diesel and motor oil. That's fresh motor oil, not used motor oil. I give up, right? I got to move on to the used motor oil. And after 37 injections of used motor oil, I start to see an increase in the breakdown, but it still meets the 8081B criteria. You see DDE pop up a little bit, DDD. You can start to see ender and ketone a little bit, but we're still functioning here. If we go for 145 injections of used motor oil, we finally get the breakdown up to about 6%, but we're still meeting the 8081B criteria of less than 15%, and it's all tied back to this very fast inlet flow, low residence time for the inlet. Not much time to break down when you have that fast inlet flow. This is what the liner looks like when you pull it out. It's filthy, of course. Surprisingly, the seal is pretty clean, except maybe right in here where the split goes, and you can see just the barest amount of dirt. So that worked out pretty well, I think. Now, if you take that same liner and you do a splitless injection in it, and the inlet flow is only 1.2 mils per minute, you can see our problem immediately, and that is we have unacceptable endrin and DDT breakdown. So for this shoot-and-dilute GC-ECD conclusions, I think that split injection can help minimize and break down and absorptive losses of sensitive pesticides. It reduced the amount of non-volatile material placed on the GC column, which is very protective too. And GC column is an expensive part for some people who are doing ECD work, so they appreciate that. It allows a higher oven start temperature, increased analysis throughput. And it's also highly reproducible when you're actually wiping the needle with the wool plug that sits up relatively high in this precision liner. Now, anybody who knows me knows that I'm apt to show conclusions for a talk and keep going on at any time. And that's what I'm going to do here. I want to show you pHs now, because we were also able to do this with pHs. pHs, it's a different situation. Some of them are very involatile, and they don't want to chromatograph out of the dirt in the inlet liner. So if I do my used motor oil thing again, and I do a splitless injection with a single taper with wool liner, I see things like benzo-bifluoranthene, benzoapyrene, benzo-GHI-pyrroline crashing down pretty quick after a few injections. This is not good because this can lead to quantitative bias. If you're not using a C13 or some sort of deuterium label for every one, you're going to have problems. And you can see you're just losing sensitivity anyway as you build up dirt on the inlet liner. And we can view that chromatographically right here and consider that more volatile components like benzoanthracene and chrysene don't have as bad a performance. But when we get up into the late eluters, the response factor has dropped down to about 20% of its original value. And that's, of course, because the dirt is building up on the wool. The pHs don't want to partition out of the dirt to get to the column prior to us turning the purge valve on. And it looks like that. Can you see the dirt on the wool, or is it too bright in here? There's dirt on the wool, trust me. Trust me, I'm from Restek, and I sell you used motor oil. Okay, we can change the liner. We changed the liner. We didn't even have to change the seal. And again, you can tell the protective effect of the wool. We didn't have to change the seal at all, and we're pretty much back to where we started. So we're happy about that. But we'd like to stay up longer. So if we go to our split injection, and we're using the 4 millimeter ID precision liner again, here's a pH standard at the start of the experiment. And here's one after 200 split injections of used motor oil. 1 million nanograms of oil into the liner. Or as Dr. Evil would say, 1 million nanograms. Yeah, well, that wasn't a very good impression. Why don't you do that next time, Kyle? See what I mean about the late eluters? Here we go. Start of experiment, orange. 200 used motor oil injections, no problem. The responses are essentially the same. We have a moderate inlet temperature. The split ratio is 10:1, so the flow through the inlet is relatively high. It keeps those things moving, and they get to the detector with no problem. Here's after another 5 million nanograms used motor oil injected in the liner, and you can see that even something like benzopyrroline out here has essentially the same response. So this, I think, is a viable technique where you have the sensitivity to do what you want. Okay, so just fill up that liner with oil. It's not a problem. It's not expensive either. If you think it's expensive, it's not near as expensive as something like a cup liner or a cyclosplitter or one of these other liners that takes a little artisan a few hours to make. It's a lot cheaper. The thing I want to finish up on, do I really even have any time left or not? I do? Wow. I better slow down. Standard reference material 2260A. This is a great standard for doing a pH experiment because it includes volatile pHs, the ones I have listed up there, things like naphthalene and phenanthrene, etc. It has important toxic pHs like benzoanthracene, chrysene, benzobifluoranthene, benzoapyrene, etc. Less volatile pHs like coronene and dibenzopyrenes. And then it has co-eluting congeners that we can try to resolve on a particular column that we're actually manufacturing now quite well. I like it for this work because of the coronene, the dibenzopyrenes, dibenzo-H-anthracene, etc., things that are less volatile, things that we think we can improve response factors over the long term for with this shoot-and-dilute technique. Okay, this is just to show you a few chromatograms of things separated like benzoanthracene, chrysene. We're pulling triphenylene away. This is cyclopentacetylpyrene. All the benzofluoranthenes separated, benzoapyrene out here. And we even do a pretty good job of dibenzo-AC-anthracene and indenopyrene and dibenzo-H-anthracene. These two typically co-elute on 5-type columns. Benzo B and J can co-elute on a regular 5-type column. Triphenylene and chrysene can co-elute on a 5-type column. So we like this column for doing this type of work. The sample that we're working with is a marine sediment from NIST again. It's 1941B. We had a pretty standard pressurized fluid extraction in an ACE. 10 grams of sediment, methylene chloride, extract concentrated to 1 mil and diluted to 50-50 with toluene. I don't know if you can see it, but it's green. It's an ugly green color. I assume that's chlorophyll or something, but it's not something that we would necessarily want to inject all the time on our system, and we're not going to clean it up at all. If I do splitless injection, and this needs a little bit of interpretation right here, because I'm doing splitless injection of 2260A here, 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 all the way down. You can see that on this axis. And then I've actually injected between those a particular number of the 1941B extract. And what we're doing is trying to build up dirt on that inlet liner to see if it subverts the performance of responses for PAHs. And for something volatile like anthracene, it really doesn't. We're actually doing relatively well with anthracene. Now, everything is a response factor versus phenanthrene as an internal standard because it's relatively volatile and seems to make it through unscathed, even if the liner is relatively dirty. But you can see some of these others are diving down right here. As you get less volatile, you tend to see a response factor change over the experiment. What happened? Uh-oh. Did I miss? That's weird. I lost a slide. Okay. I had a more dramatic slide. I should act it out. I should pantomime it somehow, but somehow it flew out. Nope. Anyway, the response factor is probably about half for chrysene. It's probably about half for BAP, about half for dibenzo-H-anthracene. It's diving down for splitless injection. For shoot and dilute or split injection, these are more straight across all the way. They're not losing response near as much as the splitless injection did. Ah, that one worked actually. Okay, this is split injection. So I'm zooming in now so you can see that there is a slight decrease for chrysene, a slight decrease for BAP, benzoapyrene, a slight decrease for the dibenzo-H-anthracene, and a slight decrease for coronene. But all in all, the system uptime is going to be longer for split injection versus splitless. Now, I hope I don't go horribly astray here. I may need to be called out on this where I exaggerated a bit, but I tried to be conservative, and I thought about actually putting this in at the start to convince you that this might actually work for some of the analyses that you're interested in, with some of the mass spectrometers that you're interested in. So I actually calculated LOQs, approximate LOQs, based on the sample amount, the final extract volume, the detection in femtograms, and then I did the math, and hopefully I did it right, and proposed what you might expect as a LOQ if you're using a 10-to-1 split ratio. And I don't think this is out of whack. I showed you 40 femtogram peaks that were no problem, so I think I could drop down lower on the ECD. I got the 25 femtograms from this app note right here as their lowest calibration point, so I suspect you could go lower here. And I'm just guessing that the PCBs are a little bit better responding on the DFS than maybe the BDEs. Did I go astray, Kyle? Were you even listening to my talk? Yeah, okay. I caught him. Anyway, I think that this is viable. And one thing I'd like to say, if we could jump in a time machine and go ahead 5 years and have Thermo tell us they just improved the sensitivity of the instrument by tenfold, that we might all be using this technique right then and there, assuming that things didn't continue to drop. Or maybe you guys are going to tell us that you've done that, made the instruments 10 times more sensitive in the tour tomorrow. No, you're not going to do that? Okay. Anyway, the final thing, and the only MSMS bit, but I promise to have more next time I speak on this, we have a TSQ 8000, and we found that it routinely achieves femtogram detection level, and we were recently doing some MSMS and some TOF-MS comparisons for MATE-T, pHs in MATE-T. And even though we use splitless injection, I'm convinced, based on what I saw, that we may be able to get by with not doing a cleanup, because we did a cleanup for working with the TOF, and using split injection, 10, 20 to 1, to easily do our work here. We could avoid a relatively extensive offline cleanup. I don't think the chlorophyll in the T was going to negatively impact the line or such under split injection conditions that we couldn't accurately monitor the pHs that we were looking for in the T. So there's a real-world application for this that we're pursuing right now. We're looking at this for brominated flame retardants. We've already done some work with pesticides in food. We're doing it for PCBs. We think that the MSMS sensitivity is going to give us some flexibility to improve our front-end reliability and introduction. Okay, so benefits: increased GC uptime, higher sample throughput, reduction of matrix change response, better data accuracy and repeatability, blah, blah, blah. You can have a copy of the presentation, and I'll shut down with the acknowledgments and thank Thermo Fisher and all my colleagues from there for continuing to put on this wonderful event. It's a great way to learn stuff. I learn so much every time I come in here. And yes, that is you on top, Kyle. Thank you.